Yeah, well, as we all know, Clementine had about a 2-month surface mapping mission in the mid-90s, but there was also considerable effort dedicated to measuring, actually searching for lunar horizon glow, with using the navigational star trackers going into shadow. The Clementine orbit was a very eccentric periapsis. Apoapsis was way out there, several thousand kilometers, and star trackers would look from shadow on a number of orbits to see if there you could spot the horizon glow. Okay, I had this in, I took it back out, but I thought it just about sums up the whole idea of the search for lunar horizon glow, what this present status is, and that is that I'm not going to go through this list, but there's been a number of sporadic observations, some quantitative, okay, some searches that have yielded nothing. So as of the present time, there's nothing you would call an irrefutable detection in quantifiable detection, right? But the search, the fun continues. The search continues. I did want to comment. These top few, those were especially the Apollo 15 chronal photographs, where those were calibrated measurements and they were fairly quantitative. A large excess brightness was seen, and if you interpret that brightness in terms of dust, then you have you would have a fairly substantial dust exosphere. In contrast to that, some recent searches, by sensitive instruments, especially LRO lamp, have turned up nothing. And Kurt Rutherford commented on that today. That search is ongoing, but as of July 12th, there's no detection. So there's a bit of a disconnect here. But moving on, this is
David?
Yeah.
Could you step back to the mic?
Oh, okay, all right.
Thank you.
Yeah, this is a typical star tracker image that you see, and in it, it's just about every kind of background like you can imagine. This has shown up at several different meetings and a couple of different posters. It's interesting because you can see the back up. You can see Earthshine there at the top. This main bright part here is the diacal light. Okay, that's not exospheric dust or lunar dust. The diacal light dominates these images that the star trackers look at. One controversial thing is this area over here. If you look at those images, your eye looks at it, and you ask the question whether there's a faint horizon glow there or maybe not. Obviously, the thing you would think of doing first then is to get an independent measurement of the zodiacal light, subtract it from the star tracker image, and then see if there's anything left over there. And that's basically what we've tried to do. Just real quickly, this is an overview of the Clementine measurements, the 2-month mapping mission. Actually, some portions of some 25 orbits were dedicated to this search, to a search for to horizon glow searches. And just a comment about those, Joe Hahn looked at CZL and critiqued these observations pretty closely. They are calibrated, they're photometrically calibrated. There are 2 limitations, though. One is the fact that the star trackers are out there several thousand kilometers, so the resolution at the limb is something like 10 kilometers. So if you have a 10 or 20 kilometer scale height dust exosphere, you may be talking about 1 or 2 resolution elements at the top. So what we did was look at 5 sequences that we thought were optimal. One thing that's important is you want to pick those sequences that had an Earth dark limb. Okay, so Earthshine was not illuminated in the limb you were looking at. That gets rid of the prospects for scattered light. And you want to look at small solar elongation angle. You want to get in there just before the sun rises or sets. In those cases, you have a very low dust illumination altitude, and you're seeing basically the full exosphere. And this shows you the 5 cases that we explored early in the mission: Orbit 66, The orbital plane was such that you'd view the morning terminator, and later in the mission, 164, 193, you're about at zero phase, and so when you look at the limb, you're looking either over the North Pole or the South Pole. That's orbit 164 and 193. And then late in the mission, you're looking at the surface sunset terminator. So as it turned out, these 5 sequences did a pretty good job of also sampling the sampling longitude. All right, okay, here are some sample images from each series. Top surface sunrise. Well, what I've done is, what you can see in all of these, once again, is the coronal zodiacal light. And what I did was add intensity contours, okay? In this case, 2 contours per decade. You can look at those numbers and you can immediately get a feel for the brightness. Units here are units of mean solar disk brightness. That's sort of standard unit to compare with. So close to the sun. Incidentally, the axes are in ecliptic coordinates. So all of these cases, you're within 2 or 3 degrees. There are images in the sequence within 2 or 3 degrees of the sun, a very small solar elongation angle, so they're favorable. Intensity of the CZL, the main contributor close to the limb, is something like approaches 10 to the minus 10, just a few times 10 to the minus 10. Okay, next question is, how are we going to get rid of that bright CZL? We need to subtract an independent zodiacal light measurement if we can. And what we've used is the thing I saw is a Soho wide field coronagraph. That's a handy instrument that has a field of view of something like almost 8 degrees. It's well suited to our measurements, to the scale of our measurements. You really have to break that up into 2 parts. The zodiacal light is both the F corona, which is the dust close in, and then on top, and then in addition to that, it's the electron scattering. It's the time variable K corona in the streamer structure. And we took a 3-month series of regular cadence, and it was possible to separate those into sort of the steady state F corona and then the time variable part. Okay, time variable part you can't do much about, but the steady state F corona you can subtract from the images. Okay, here's the different images. I'll just step through them quickly. These were a couple of images, 2 or 3 images each from our 5 sets. Here's the sunrise limb, north polar, south polar, and 2 on the sunset side. You look at this, you see, well, there's these extra, there's this straight, we won't call it straight light, but there's this extra light that sits above the lunar horizon. And the first, if you look at that and compare it with, you look at that, then you look back at the chronograph images, you see that it's about, these are the right brightness, the brightness you'd expect in the difference images to be coronal streamers. They're obvious in several of the images, and some of the other light blotches there are just sort of the excess light in the K corona that comes out 2 or 3 degrees from the sun and then just sort of disappears. The bottom line is that after the image subtraction, we can explain just about all of the excess light there. I should also give you the scale from one end to the other. It's a couple of times 10 to the minus 11. So the brightness of these things is of order 10 to the minus 11th B sun. So there's, at first glance anyway, well, there are a couple areas here that are questionable. We're not sure whether that's K corona or whether that's or whether it's something else that's not included. how do we, okay, the next step is, how do we convert this excess light bit after we've accounted for the K-corona stuff? How do we convert this to an upper limit on dust abundance? One way to do that is if you look at this, actually take a look at the noise level there. That would be given by this granulation, which you see in several of these images. You can sort of take this granulation, take the RMS fluctuation, and then ask yourself what dust brightness, what limb brightness would you have to start to come above that granulation? Use that as a detection criteria. So we've done that. I took several of those images, and the numbers vary by factors of 2, but 3 times 10 to the minus 12 B sun is a reasonable estimate for that fluctuation. You can ask the question, what line of sight a upper limit corresponds to that? Okay, and we can do that with just putting a few modeling parameters. We know the geometry. We know the per grain radiance. That can be obtained using me theory, grain size, and knowing this visible wavelengths and small angle scattering. Add an extra factor of 2 for optical blur, because if you have a 10 or 20 kilometer blur, functionally 10 kilometer exosphere, then there's a little degradation there. And if you put that, you get to the bottom line, you get something like 1,000 grains per centimeter square. So, last slide here. Summary and conclusions. We looked at we think are the most favorable star tracker images, and there's no detection of anything you would call a horizon glow. Nothing obvious. The equivalent grains along the line of sight would be less than 1,000 if they are 0.1 micron grains. There's a bit of a disconnect here with the Apollo 15, the excess brightness observed in Apollo 15. That's 10 to over a couple of 100 times larger. So there's Clementine didn't see anything. Apollo 15 saw a rather bright excess light. Just real quickly, the possibilities. Probably not a UV photo emission. Wasn't that different? Which could launch dust. That wasn't that different in those 2 cases. Possibly active meteoroid streams. Topography might exert a strong influence. Okay, it might be very, your observation might be very sensitive to topography, not known. And then last, we have to acknowledge that this is basically one measurement or one measurement series. There could have been, it's possible there could have been calibration error or stray light, although that was studied pretty much in detail. This will be resolved one way or another with the LADEU visit LDX measurements. Thank you.